We'll now do the proof details of the lemmas we covered in the second part of the walkthrough video. To prove that the algorithm from the first part of the walkthrough video correctly outputs every possible combination of a list, we will have to show that every element in the output list is a distinct ordering of the input list, and the output list has a size of n factorial. Notice that I have combined first two lemmas from the second part of the walkthrough video into one. Feel free to do something similar if you do prefer. The sample grading rubric breakdown for the proof detail is similar to the proof idea. Here's the proof detail for lemma 1, using induction on n, starting with a base case. For n equals 1, when the list has a size of n equals 1, you reach the base case condition of length of the input list equal to 1. Every element in the output list is a distinct ordering of the input list. We will come up with an inductive hypothesis. When n equals k, any entry in the output list is a distinct ordering of the input list. Here's the notation for inductive stats. Let Li be the list returned recursively for the ith element in the recursion. Let Si be the I cross product of Li. Let the output list be the union of I, Si, as it is the atom of all final concatenated combinations. Notations are introduced here to make it easy to refer to various lists in the rest of the proof detail. Moving forward to inductive step. With an input list of size k plus 1, this algorithm utilizes a for loop to traverse through all k plus 1 elements, where any element with index I will not be equivalent to any element in index j, for I does not equal to j. For the first element I in the input list, the algorithm removes the element I and passes the remaining list into a recursion. The recursion will return the list at Li. Si will eventually be built up with a concatenation of the current element I and the Li at the end of each recursion. With inductive hypothesis, Li are distinct throughout the process. Therefore, all entries from the same Si will also be distinct since Si is equivalent to I cross product of Li. With the inductive hypothesis, we can assume that the probability holds for the rest of the k elements. By definition of the algorithm, Li does not contain the element I due to the removal of the current element before passing it to the recursion. Therefore, all combinations in union of I, Si, and input list are primitive. The first element of each ordering in Si is I, and each ordering in Sj is j. Since I does not equal to j, all ordering in Si and Sj have distinct first element and are distinct as ordering. Since Si is distinct, and when I does not equal j, Si and Sj will also be distinct. The extension, the output union of I, Si will also contain all distinct combinations. Recall that we already argued in the previous paragraph that entries in Si for fixed I are all distinct. With proof by induction, we can conclude that lemma 1 holds. Here's an L3 version of the proof detail for lemma 1. The base case and the inductive hypothesis is the same, but the inductive stat is different. The inductive stat does not include a justification for distinctness and does not define the variables. Here's an L2 or L1 or even L0 version of the proof detail for lemma 1, copied from the proof idea. Also, a penalty will be given if you copy over the proof detail to the proof idea. Here's the L5 version of the proof detail for lemma 2, using induction on n, starting off with a base case. For n equals 1, when the list has a size of n equals 1, you will reach the base case condition of length of the input list equals 1 and the exact list will be returned. Since 1 factorial is equivalent to 1, the base case holds. We will then develop an inductive hypothesis. When n equals k, the output list should contain k factorial numbers of combinations. Moving forward to the inductive step, when the list has a size of k plus 1 elements, the algorithm will iterate through every element in a for loop. The current element within the for loop will be removed and the recursion will be running with the remaining list. The first element of the for loop will create k plus 1 possible combinations through recursion. Since we argued that all Si is distinct in lemma 1, and according to our inductive hypothesis, we can assume that this algorithm works for n equals k elements, creating k factorial combinations. Therefore, k plus 1 times k factorial is equivalent to k plus 1 factorial. Numbers of combinations will be created from the algorithm of k plus 1 input. Hence, with proof by induction, lemma 2 holds. Notice that I've used notation from the previous lemma proof. You're only allowed to do so if they're from the same part of the question. For example, using notation stated in a different part of the question or from proof idea is not allowed. Also, compared to the proof idea, we explicitly discussed how the algorithm traverses, the application of inductive hypothesis, and the mathematical equation in more detail. Here's the L3 version of the proof detail of lemma 2. The only difference between L3 and L5 version is that L3 version provides a vague argument. No justification is provided for the effect of the key ideas highlighted in yellow here. We can really tell how the idea supports the argument. This version might even lead to an L2 or L1 depending on the assignment. Here's the L2 or L1 version. The reason for the reduction are incomplete proof, missing base case, missing inductive hypothesis. This might sometimes even lead to L0. Of course, one could do a proof not using proof by induction, but here the proof is structured like a proof by induction, and hence it was created like a proof by induction. Moving forward to a conclusion, in CSE 191, you have seen that in permutation there are n factorial possible combinations can be generated with n elements in the list. Therefore, by lemma 1, everything outputted is a permutation of input list, and by lemma 2, this algorithm outputs n factorial entries. All the required permutations are indeed in the output list, hence proved. This concludes the video of proof idea versus proof detail. Feel free to post questions on Piazza or attend office hour if you have any more questions.